So welcome to our third lecture, dealing with metal complex chemistry, that is, coordination chemistry. And now we have another topic to take up. We've talked about the four compounds that Werner was using to establish his idea of coordination chemistry in primary and secondary valence, which we now call oxidation state and coordination number. And of course, the first one, the hexaamine cobalt 3 chloride, and the cobalt pentaamine monochloro cobalt chloride. And for those two, it's fairly simple and straightforward. We run into a problem with the next two, though. The next two, of course, have 4 ammonias and 2 chlorines in the coordination sphere. Tetraamine dichlorocobalt 3 chloride. The trouble is, of course, they can't both be tetraamine dichlorocobalt 3 chloride because they're different colors, which if nothing else means they are absolutely different compounds. And the first rule of nomenclature is that a name must identify one specific compound. And since these are two different compounds, they can't have the same name. But they have the same formula, but they're different compounds. Which, of course, brings us to the topic of isomers. Isomers are compounds that have the same chemical formula, but are different compounds, which means they have to have a different arrangement of the atoms in some fashion. We run into several different kinds of isomers chemically. The simplest one, of course, are just plain structural isomers. That is, they are different compounds. The bonding and arrangement of the atoms is different, and they just happen to have the same formula. For example, dimethyl ether and ethanol are structural isomers. They're just obviously completely different. In the ether, both of the carbons are bonded directly to the oxygen, while in the ethanol, the carbons are bonded together, and the oxygen is bonded to only one carbon, and it's bonded to a hydrogen as well. And so, not surprisingly, those are different compounds, and they would have different properties. That's not going to help us in our case here. In our case, both of the complexes involve 4 nitrogens and 2 chlorines being bonded to the cobalt. All the atoms and all the bonding is the same. So these are still isomers, but they're not structural isomers, they're geometric isomers. That means they are different, not in the bonding, but in the arrangement in space of those bonds. So what is that 3D arrangement in space? Well, we already know from Vesper what arrangement 3 pairs of electrons around a central atom want to go into. They go into an octahedron. And this is, in fact, what happens in the cobalt hexaamine complex. All 6 of the ammonias end up in an octahedral arrangement. In the pentamine chloride, they're still in an octahedron, only in this case one of the sites is occupied by the chlorine. But there aren't any isomers because, of course, all 6 of the octahedral sites are identical. And so simply have a chlorine in one of them. It's different for the tetraamine dichloro complex. Once we put one of the chlorines in, we get 2 different places. The site directly opposite in the octahedron, and the sites that are in the plane right next to it. And so we get cis and trans isomers. Where the 2 chlorines are together, we get cis. Where they are apart, we get trans. So we talk about geometric isomers. The version where the 2 chlorines together are cis, so that would be cis. Tetraamine dichlorocobalt 3 chloride, and the ones where the chlorines are on opposite sides of the octagon, they would be trans tetraamine dichlorocobalt-3 chloride. The ammonia, of course, has only one pair, and therefore it is the only thing it can use to donate in forming the coordination bond with the metal center. We talk about it being monodentate. Mono being the Greek word for one, and dentate, similar to the word dentist, meaning bite. And so ammonia is a one bite that is a monodentate ligand. But a number of common ligands, in fact, have a choice. They have more than one lone pair which they can use to donate to form a coordinate covalent bond to the metal center. These are known as ambidentate ligands. That is, either bite. They can bond in two or more different ways. Cyanide, for example, has two lone pairs, one on the carbon and one on the nitrogen. If it coordinates with the carbon, that would be one isomer. If it coordinates through the nitrogen, since the bonding is different, that would be a different isomer. And so we talk about linkage isomers. In the old days, they indicated that the carbon was coordinated by using cyano for the name of the ligand, and when nitrogen was the linkage, they talked about isocyano. Eventually, they decided that it was silly to make up a new name for the same ligand simply because it was bonded to different atoms, and the newer nomenclature simply uses the name cyano and then indicates whether it is with the carbon or the nitrogen that is bonded. You have the same thing with thiocyanate, and you run into the same thing with nitrite as the ligand. If nitrite is bonded through the oxygen, it is called nitrito. If it is bonded through the nitrogen, it is known as a nitro ligand. You can, for example, make two different compounds, which include 5 ammonia molecules and 1 nitrite, one of which is yellow, one of which is red. Now, these aren't structural isomers. Everything is bonded the same way to the same things. And of course, they're not geometric because we said 5 amines and 1 odd is always going to be the same. What is different is who the nitrite is bonded with. Where the ligand is bonded through the nitrogen, we get a yellow compound, pentamine nitrocobalt-3. Where the nitrite is bonded through the oxygen instead, we get a red compound. That's pentamine nitrito-cobalt-3. And these, of course, are what are known as linkage isomers. Some ligands not only have more than one place where they can form a covalent bond, but they are actually capable of using more than one site to form a covalent bond. We talk about bidentate ligands. That is, the ones that can take 2 bites. They can end up taking 2 bites in 2 different ways. For example, they could simply have 2 completely different sites that can bond. For example, we have this compound, ethylene diamine. And this is basically 2 nitrogen or 2 ammonia molecules linked by a 2-carbon chain in between. One of the nice things about being inorganic chemists is we can ignore what the organic chemists think the correct name for that compound would be. It's referred to by inorganic chemists as ethylene diamine, and it's often abbreviated in chemical formulas as simply an EN. So if you see a small EN as part of a formula, they're referring to ethylene diamine. Alternatively, a single atom can use 2 of its lone pairs to form a bridge between 2 metal centers. In this compound, technically di-mu-chloro tetracarbonyl dirhodium 1, The chlorine is using two different lone pairs to bond to each of the two rhodiums. Some other common coordination ligands, including acetylacetonate, known as acetylacetonate auto, of course, often abbreviated ACAC as a formula, and oxalato, that is, oxalate, is also a common bidentate ligand, both of those of which can bond through both of their two oxygens. And finally, we get a special case. If you start with the ethylene diamine and start replacing its hydrogens with acetate groups, you can in fact end up with 4 of them on the ethylene diamine. That is ethylene diamine tetraacetate. And the point is the nitrogen has a lone pair. One of the oxygens on each of the acetate groups can also act as a ligand. And so that in fact has 6 sites. It's hexadentate. And it's often abbreviated as EDTA. So if you are running into a formula that includes EDTA, that's ethylene diamine tetraacetate, as a ligand. And it is 6 coordinate. And that brings us to the end to today's lecture on coordination chemistry and metal complexes.